quick hi. My name's James Bourne, CIBSE Home Counties North East Chairman, and we're really pleased to be able to do some of these events. We've got a great following now, and it's coming up really well. We're getting great attendance on some of these, more so than our live face-to-face events, as everybody knows. These are easier to get to, and it's good. So what I do want to do is just promote the fact that we are still looking for more people to help join CIBSE and join the committees and carry out some of these tasks when we do get back to face-to-face. There'll be some feedback forms that come out with the CPDs at the end of this next week, or I don't know when Julian's going to do that, but that'll come out shortly. And so, just get in touch if you do want to get more involved with CIBSE. It's really appreciated. Other than that, I'm just going to hand straight over to the team at Bosch who are going to do a presentation this afternoon on heat network design. So it's over to Angus and Pete. Over to you guys.
Thanks very much, James. Cheers for having us, everybody. Very much appreciate all of your time. Quick little intro. I suppose Angus Turner here from Bosch Commercial Industrial Heating. I'm one of our business development managers, and we've got my colleague Pete Mills, who heads up our commercial technical team as well with us. As James mentioned, quite a few of us here today, and that number probably only going to creep up. So we shall crack on with the presentation to try and leave some good time at the end for questions and answering anything that you might have, little queries, big queries. If you've got any questions on that front, please fire them into the meeting chat box, and I'll be able to keep an eye on those there and make sure we can answer them all in due course. Other than that, Pete, are you good to crack on?
Yeah, I'm just going to chance my arm with the video for a few seconds just to say hi to everyone and then promptly turn it back off because I live out in the wilds of Norfolk and broadband is a little bit challenged out here, and sometimes that just pushes it over the edge. So I'll, if you'll excuse me, I won't have the I won't have that on as we go through. If everybody could perhaps just remain on mute until we get to the end with the questions, that just helps a little bit. We don't get any feedback and things like that going on, then that'd be great. So welcome everybody to this Bosch CIBSE CPD looking at heat network design considerations. This is very much based on CIBSE's CP1 Code of Practice for heat networks in the UK. And probably many of you know, I would think in this group, that CP1 has actually been up for revision for quite some time now. We were expecting out actually probably the latter end of last year and then at early points in this year. And I think we got pretty good news recently that it should be coming out imminently, really. So it's expected to be CP1 2020, as long as we do get it out in the within 2020, that is. Quite a lot of changes really coming in the new version, and this presentation that we're going to go through this afternoon was put together right back in 2015 when CP1 first came out. So as you can imagine, there's a number of things within this presentation that are now getting out of date, and so we've got a new presentation ready to go, but of course we can't use that until the actual CIBSE document is released. So I'm going to try and point out some of the key changes and differences as we go through this presentation, really, which hopefully will be of use to people that are already involved in heat network design. The presentation itself was put together really focused on people that are perhaps coming to heat network design for the first time. So if you're already a very proficient heat network designer, some of the things in here might be at a lower level for you. But as I say, hopefully there'll be enough interest in seeing what's going on with CP1 and what the key changes are. So we're going to go through, first of all, just a brief introduction to heat networks. I'm sure everybody knows what a heat network is, but I'm really just looking at what's been going on recently and where heat networks sit within the decarbonisation of heat. Then we're going to look at things like calculating flow rates and really consider a kind of hypothetical design, going through looking at the energy center and calculating buffer sizing, heating plant and that sort of thing. And then we'll move on to look at how we could introduce low carbon renewable heat, and then a few hints and tips on how to refine the design as we go through. So heat networks, well, as I say, probably everybody knows what a heat network is. I think it's interesting to see where heat networks fit within the decarbonisation of heat and the strategies. If we look back historically over governments' strategies for the decarbonisation of heat, you'd see that at a very broad level, it pans out into perhaps three different pathways. So we've got, on the one hand, we've got the all-electric pathway, which typically leads us to heat pumps as being the main technology there used. Some significant challenges there in getting the market going, but also concerns about how the network, the existing grid, etc., would be able to cope with that. So some significant challenges in all sorts of areas there. On the opposite side, on the other hand, we have the decarbonised gas route, which really leads us to hydrogen with blends and then eventually 100% hydrogen, something that we're very much involved with through Worcester Bosch, involvement with government's High for Heat scheme, etc. Looking very promising, but still something that's just over the horizon at the minute. And of course, in the middle pathway, we have heat networks, and heat networks, I guess, really seen by government as a kind of no regrets policy, something that they can be getting on with now, something that is easier to decarbonize in the future, even if they come into existence not perhaps using a high percentage of renewable heat from day one. Because they are agnostic of the energy coming in, they are much easier to decarbonize in the future. And we've seen from Scandinavia that heat networks can really be a useful tool when they're done correctly, when they're done right. But I think going back historically, there certainly has been some issues going on with the design and implementation of heat networks in the UK. I think if we go back perhaps just before the CP1 first came out around 2014 or so, we had various public reports and things coming out. We had the Which report that came out around that time, which made fairly uncomfortable reading for anybody in the heat network industry, where tenants were suffering in certain situations through poor service levels and the like. I think CP1, although it was already in the minds of people, I think CP1 certainly had a boost in terms of coming to the market as a bit of a response to some of the reports and bad press that was going on within the industry at that point. And I don't think there's no doubt really that CP1 has certainly done a lot to help the industry going forward. But I think, some of the problems have remained, and some of these issues that really stem from poor design and result in high heat losses in district heating schemes and heat networks, and leading to inefficiency, etc., was still going on. So back in 2017, government asked the Competitions and Markets Authority to get involved, the CMA, to have a look and see if there was something flawed within the industry, some kind of problem. To cut a long story short, CMA came back to government and really made a few recommendations. The main ones being that it recommended to government that it should consider regulating the industry, and we've seen the first kind of moves to that with the consultation on the heat networks market framework earlier in the year. That consultation's come to an end, and government is now considering what to do about that and how to do that. I think the other thing that really CMA said to the industry was, or discovered really, that there were some genuine technical issues that were going on, and it urged the industry really to try and address these issues rather than waiting around for regulation to come along and to kind of prompt us to do all these things. As I said before, heat networks can be a great tool, but they are also a natural monopoly, and that means really that if we get them wrong, if we get things not working correctly, then that leads to poor outcomes for customers, and they are pretty much stuck with what they've got. There aren't very many solutions or alternatives for people that are on a heat network who might want to opt out of it. So it's really important that we get them right. So as I said, CP1 came about in 2015. As a bit of a reaction to this, it was a collaboration really mainly between CIBSE and the ADE, which is the Association of Decentralized Energy, which is the main, I would say, trade association in this area. They came together to produce this this document as CIBSE's first code of practice as well. You know, first, hence its CP1 name. So it's a little bit different to other CIBSE guides that we're perhaps used to seeing out there. Being a code of practice, it looks at more at the stages of how to go through procuring and looking into the feasibility, etc., for a heat network. I think there was some criticism when it first came out that it wasn't a technical guide, and there was perhaps a need for technical guidance, and that was missing at that time, definitely. I think CIBSE and ADE subsequently came back and had a go at trying to put together a technical guide, but that ran into the sand for various reasons, people not being able to kind of agree on the approaches that should be taken, etc. And I think it became, you know, quite difficult to get anywhere with that. CIBSE also had a go at this, and I think for various other reasons that also petered out. In the meantime, a guy called Chris Parslow actually put together a technical guidance document, which I think he was the main author for the CIBSE guide. And I will say I've got no connection to Chris Parslow, but I think his guide is probably useful, you know, stopgap if you're looking for some good technical guidance. And I understand that CIBSE are looking to actually adopt that guide along with the you know, the next version of CP1 2020 as and when it comes out. There's a lot of significant changes within CP1 2020. I think the main driving force around it has been to make CP1 more technically verifiable, because there is certainly a need for that within our industry, that we can you know, tick off, if you like, and check that certain stages have been done correctly. And I understand there will be other documents that are released with CP1 2020 that will help this, kind of Excel-based documents that will kind of, you know, give a basis for this technical verification. It's certainly something that I think has been muted within the kind of looking at the regulation side, that there is this need for this technical verification, and also to help draw in more investment through increasing investor confidence that you're going to get good outcomes here, really. So yeah, we await CP1 2020, hope that it's coming out fairly soon, because I think, as I say, there's going to be some significant changes in there, particularly in the area of like acceptance testing, which I think we'll talk about a little bit more as we go through. So from this point on, I just want to think about a hypothetical design that we might need to do for a small heat network, and just think about some of the key, well, really pick out some of the key stages that we go through in design, and just look at a broad approach to what we need to do there. I think certainly some of the learning really has been that the approach to heat networks needs to be, or heat networks design needs to be quite different to what we do with standard mechanical design, in as much that there's this kind of tendency, or has been this tendency, for mechanical design to perhaps slightly, you know, over design things and oversize things, because that acts as a bit of a insurance policy, you know, making, well, the kind of mindset is that this that gives them a little bit of margin for error, as it were. But I think when it comes to heat networks, experience has shown really that there's a real need to be designing quite tightly, because if we start to oversize things and over egg things, really, then this leads to problems in the efficiency of the network. This is the route really where we go to high heat losses and the like. So I think the first message here is really to be sensible about what the actual requirements are for the, you know, the domestic hot water flow rates, the heating requirements and the like. Because if we are sensible about this, and if we put extra effort in the front end, either through better modeling of what the requirements will be, or if it's an existing you know, network or property, sorry, that's going to be put across to a network, then we could perhaps consider some better metering and things like that going in. certainly the more work we can put in at the early stages will pay dividends really going forward. I think some of the other things that need to be considered here are really around thinking about the operational costs and efficiencies and how they will play into the overall financial balance really of the network as it goes forward. It's very much a need to think about whole life costing here for networks. There's obviously this tension between capital costs and whole life costs really, but certainly when you're designing a heat network that's going to be lasting maybe 40, 50 or a lot, many more years after that, hopefully, whole life costs really come into it and certainly outweigh a lot of the things. And I think that's important to really consider at the design stage. I think one of the other key learning things that's come out of experience so far is that sometimes there's this disconnect between what the design intent is and how things actually get built out, and how certainly at the commissioning stages how that communication happens. I think sometimes because of the procurement processes that we have here in the UK, that can become quite fragmented, and so design intent can be lost. And I think it's one of the areas that CIBSE really want to do here in terms of helping this whole process. So this is partly where some of these new documents will come in, so that the designers right from the outset can start to populate these documents that will find their way through the various processes and hopefully come to the people at the end of the process at the commissioning stage, where a lot of things end up going awry at that stage really. So it's really important that we join the front end with the back end really of these projects. But I think overall the message here is just be realistic about what you're designing to, because if we oversize, that's where the problems come around and the issues start to develop. So if we were going to think about our design for this small heat network, then perhaps not a bad place to start would be to be looking at the heating in the apartments. I called it the secondary heating here, but that's actually been redefined to the tertiary heating system. But I will perhaps continue to just refer to it as secondary for this presentation anyway. When we think about the heating, CP1's original advice was to just calculate your heat losses as normal. But I think certainly the data that we see coming out of heat networks now, we're starting to see that is leading to oversizing of heating. So the advice within CP1 2020 will be that there's two routes that you could potentially follow. You could either calculate your heat losses as normal, but then apply a diversity to the heat losses. And they've identified a Danish standard called Vormstabby, which could be used and actually has been used by a lot of the larger heat network operators in the UK for some time. So it's pretty well tried and tested. So you could use that diversity method, or the alternative method that they're pointing out is that you could calculate your heat losses, but don't allow for unheated, unoccupied spaces either side of where you're calculating the heat losses for. So assume 100% occupancy and think more as a block really, and hopefully that will also help you reduce your heat demands and therefore get closer to what the reality is really. The advice remains really to optimize for low temperatures, because lower temperatures on the network help the overall efficiency. I mean, certainly general guidance has been around trying to keep your return temperatures below 40 degrees if you can, because the more that we can reduce those primary temperatures, then the less heat loss that we're going to have on the system. The guidance remains around radiator systems here to be designing to 70-40, but I think there's been some problems with that really in practical terms, because I think particularly with new build, where you've got very low heat losses and your radiators become very small and your flow rates are quite small as well. If you're trying to keep those very wide delta T's, then it actually becomes quite difficult to try and balance up radiators. So I think you will see a lot more people perhaps coming nearer to 60-40, so 20 degree delta T, to make things a little bit more practical. There's also advice really in the it's kind of been beefed up really around radiators in terms of not going for these bottom opposite end connections, but go for top and bottom opposite end connections to make sure that you're getting the best out of the radiator in the first instance. Then to consider things like these presettable TRVs, where the flow rate can be preset, and they obviously helps the whole balance of the system. And then I think you also see some people fitting return temperature limiters rather than the lock shield valves. If you've not seen these, they're a bit like another thermostatic radiator valve, but they limit the return temperature coming back. So for argument's sake, you can set them to 40 and they will limit the flow unless the temperature is down below 40 degrees. And that really helps with the kind of overall strategy of balancing up your secondary heating in the apartments. So I've laboured this quite a bit, and you might be thinking, well, why is all this important? Well, I think when we look at particularly the acceptance testing regime that CP1 2020 is advocating, where you will have to probably at least do 10% of the apartments within a block like this to do acceptance testings on to make sure they're meeting all the design criteria, and maybe in some circumstances you would do more than that, and maybe even 100%. I think experience shows that a lot of the problems with high return temperatures emanate from the heating side. Generally on the hot water, we're running up against cooler temperatures on the cold water main, and the return temperatures that come back are never in excess of 40 degrees. But on the heating side, that's where the problems come from. And I think this will be a lot of the focus of the acceptance tests going forward. So it's well worth putting some extra effort into this area ahead of time, because it will pay dividends hopefully at the back end of your project when you're trying to get everything through those final acceptance testings. As I said before, 40 degrees is usually as the kind of guidance for return temperatures from CP1. There is some requirements actually within building regulations here when you look at communal heating, and so you're already supposed to be coming below 50 degrees on your radiators anyway, and 40 degrees on your hot water. So I think where CIBSE CP1 is just kind of beefing up those requirements anyway. Now, of course, if you can use things like underfloor heating or whatever, then you could be at an advantage there, because your return temperatures will be naturally lower. But, we know from a lot of situations, particularly retrofit, that can be quite challenging to introduce at times. So I think a lot of the schemes do tend to end up with radiators. So I want to just turn to the domestic hot water side now. I think I know I've kind of already touched on it here, but I think, the key thing to take away from this is to be realistic about what your actual requirements are. I think we've seen in the past, perhaps not so much now, but we've certainly seen in the past that there's a lot of oversizing going on, and we went through a real phase where people were perhaps wanting like 100 kilowatt HIUs and things like that, and you think, well, what on earth are you doing with these huge great HIUs, to require these massive flow rates? And I think it has been a problem for some time now, and CIBSE have tried to address this in the new version of CP1. There will be, first of all, there's a piece of work that was adopted from by Hugh Blakewell, actually, I think he's from Islington Council. He did a nice paper really where he looked at combi boilers as a proxy for heat interface units, and said, well, look, if I was going to do this size of apartment with this number of beds and bathrooms, I'd only be using a combi boiler of a certain size, maybe 28 kilowatt or 24 or whatever. And so you could kind of use that as a proxy for your heat interface unit. And so they've adopted some tables from Hugh's work and put them into the new document, which I think will be a good starting point if you've got to perhaps have that conversation with your client, maybe if they're thinking they need really high hot water flow rates or something like that. I think the other thing that will be useful as well is that the CP1 2020 adopts some of the flow rate guidance from NHBC, really, and that those tables have been used in there, so that there's good alignment between what CIBSE is saying here and what NHBC are also saying. So I think that should begin to help maybe that area. There's also been an awful lot of discussion around domestic hot water temperatures recently, particularly in relation to heat networks. And CIBSE actually put a separate team together or committee together purely to look at domestic hot water temperatures and how far could they really be realistically reduced to, because in the original version of CP1, we had this guidance here that you could go as low as 50 degrees because that kept you in alignment with HSC ACOP L8 and HSG 274, which was great. But I think at the time you then saw NHBC saying, well, actually, we need 60 degrees at the kitchen sink. And you also saw some water authorities that were kind of misunderstanding the whole situation here and requiring higher temperatures and things like that. And this is important because the domestic hot water temperature often becomes the limiting factor for how far you can bring down your primary temperatures. And so the lower we can go, the lower we can keep those primary temperatures and the more heat losses we can hopefully reduce. To cut a long story short, I think we've certainly seen alignment now from NHBC and CIBSE around 50 degrees, and that certainly seems to be where they've come to and will be adopted, which is really good news. I think we're also expecting that there will be this guidance document come out from the CIBSE group looking at domestic hot water temperatures, which I think actually quite nicely dovetails with the data that we get out of the BSA HIU testing regime, because there we're testing on kind of flow rates hitting 45 degrees, and it certainly looks like, I've not seen the actual details of this document that's coming out, it certainly looks like that will be using a similar temperature, and hopefully that will help the way you design around this, because you can kind of tie those data and this method together. Just a couple of other quick points on domestic hot water, really. The first thing is, I think, consider the position of the HIU in relation to the outlets, because certainly experience has shown that probably one of the key issues that come up from tenants has been around speed to get actually hot water at their outlets, really. And certainly there's a number of factors here. Obviously, one of them is how quickly your HIU performs and on all that side of it. But you know, another factor here has been very long pipe runs from the HIU to the outlets, and also people at times perhaps oversizing pipe work, thinking they're doing the right thing, increasing the volume, and of course then that takes a lot more time to run off. So really worth kind of considering what you're doing here. If you've got any leeway over where your HIU is situated in relation to the outlets, and also thinking about your primary side as well, then it's well worth giving that consideration at this stage. And we'll touch on this again just when we look at the layout of the network as a whole. And then finally on here, I just want to quickly mention summer bypasses, really. Summer bypasses are devices that ensure that you've got good primary temperatures there available at all times of the year, so that if somebody goes and puts a draw on the domestic hot water side, it reduces your delay. But I think within the industry, there's a lot of different schools of thought, really, around summer bypasses. Some people say, well, actually, I could design a very nice heat network without summer bypasses if I arrange my pipes in a certain way, and reduce, my losses, because I haven't got elevated return temperatures coming back, which is great if you can do it. But I think probably in the vast majority of heat networks that we've seen designed, some form of summer bypasses are used just to maintain that temperature there. But my point really is it's one of those areas that you should perhaps consider in your design right from the outset, and think about whether you can employ some kind of strategy around that, because there's no question, if you can reduce the number of summer bypasses and the temperature from your summer bypasses, it will certainly help the efficiency of your network as a whole. So once we've decided on our hot water side, we know what our flow rates are, we know what our operating temperatures and things are. We will need, within our design calculations, we will need to consider a diversity to use here. And I think one of the key things that CP1 did when it came out in 2015 was really to standardize the diversity standard that we use, and it opted for this Danish standard DS439, which is the orange line on this graph here. And I think when the kind of consultation came out on the changes to CP1, which must be nearly 2 summers ago now, I'm trying to remember when it was, but it's some time ago, when that actually came out for the first time, there was another standard that was proposed based around the British standard for consideration, really. But I think there was a number of, or a certain amount of feedback that came back from the industry, really saying that actually they felt that we really needed to remain with DS439. But I think what's been discovered really is that the kind of broad method that was outlined in CP1 originally relating to DS439 was actually a method that is really designed for plant sizing rather than pipe sizing. And so what's been proposed really, and what's coming out in the next version, is that we stick with DS439, but we'll actually use the alternative method in there, which is designed for pipe sizing. It's a little bit more complicated. It's more of a 2-stage method in a way, in terms of that you consider the diversity within the apartment as a whole and the outlets and the occupants and things like that. And then you consider the diversity across the network as a whole. So it's a little bit more complicated, but I think CIBSE have done a couple of things to help people here. First of all, the tables that they've adopted from NHBC around flow rates for different apartment types will help you really in that first stage, because it gives you a standard benchmark. And the idea really is that you would perhaps adopt that benchmark, or if you need to move away from that, then you'd have to justify why you're moving away from those benchmark figures. The second stage, there's a whole new appendix that's actually come in CP1 2020, a very nice piece of work done by Fairheat that gives a proper worked example that you can follow through to see exactly how the diversity should operate. So I think that will be a useful thing. So a little bit of a change, a little bit of something different to get used to, perhaps a little bit more work, but I think overall an improvement of the situation where we are today, because it's, you know, we know from meter data that comes back that DS439 is still slightly oversizing, and so that does need to be corrected. So we've got quite a bit of our information together, but we need a little bit more information before we're ready to start doing any calculations. And we need that information really from the chosen heat interface unit that we're going to be working with. So you could perhaps look up this information from manufacturers' manuals and data tables and things, and some manufacturers have these nice graphs that you could perhaps work it all out from. Can be a little bit fiddly, and perhaps there's times when you're left perhaps thinking, well, I'm not 100% sure whether I'm doing this accurately. So my advice really is to just go to the manufacturer directly and let them know what criteria you're designing to, and get the good data back, accurate data back from the manufacturer really, so that you can plug those figures into the design, because we would need to know about the return temperatures coming back and the kilowatt ratings and things like that if we are to calculate our flow rates and things properly. So quite an important stage, I think. So we're nearly ready. We've got quite a lot of our information together. We're nearly ready to do some calculating of flow rates, but there's one more thing we've got to consider before we can do that really, and it's to think about how our network is laid out. Experience has shown really that certainly a huge amount of the heat losses actually seem to occur on these lateral runs that are typically employed. All sorts of different reasons for that, really. I think they don't always tend to get installed particularly well and insulated well. Sometimes, you know, you get all sorts of tortuous runs that end up having to be made. So CIBSE's advice has always been really to try and reduce those lateral runs if you can. And their advice really has been around thinking about, could you employ more risers rather than laterals, and to split it up in that way. That's great if you've got, you know, service ducts and things available, but you know, we know sometimes by the time mechanical design gets to the likes of yourselves, then maybe you know, you're already stuck with what the architect has laid out. But it's certainly worth considering, and also worth considering about, could you really reduce these lateral runs by kind of stacking around the risers, because we've seen that that is a very good way of employing a heat network, because you really reduce your lateral runs significantly. There's a lovely, I think it's the kind of new table that's going in CP1 2020, which gives a breakdown of the heat losses that come off of a typical heat network, and the laterals account for 70% of the heat loss on a heat network. So it's really an area to focus in on, because that's where you're going to get the best effect. And we've certainly seen examples where people have managed to stack HIU around risers and have actually reduced their heat losses by over 50%. So it's, you know, really significant, because heat loss is the thing that you're continually battling against, really, as a designer. So something to think about there if you've got that flexibility. And you can also then think about strategies around your summer bypasses and things, you know, because if you've got very short laterals, then it's less important that you have a summer bypass on every HIU. So all sorts of things that you can employ there if you've got that flexibility. So finally, we know how a heat network's going to be laid out, and we can start doing some calculations for flow rates. Now, there's different ways of doing this, of course. I'm just in our very kind of simple example here, we've just got a kind of method that's been out there for many years, I guess, of assessing your flow rates for each individual leg. And so on the right hand side of this equation here, we've got the flow rate that we're going to need for dealing with the heating load. And in my very simple design here, I'm assuming that actually we've got to allow for all of the heating coming on at the same time. Now, of course, CIBSE's advice now is to use a diversity factor there. And if we were going to do that, we would be putting a diversity factor in front of that part of the equation as well, and applying that for the number of heat interface units that we got on any particular leg of pipework. Over on the left-hand side, we've got the flow rate that we need for the domestic hot water demand. And here, of course, we will be applying a diversity to each different section. So we can work our way back from the extremities of the network. And of course, we know what the flow rate requirement is for the first HIU, because we can get that from our manufacturer's data. As we go further back, though, we can then start to apply a diversity factor. So this, when we're calculating this section here, we'll apply a diversity factor that's associated for 2 HIUs, and then as we go back here for 3 and 4 and so on, and we can work our way back through the network in that way. So from out of that calculation, we will get a diversified flow rate, and we can then go to look and do an initial pipe selection. Now, CIBSE's guidance in the original version was that we should look to select our pipe initially on no more than 250 pascals per meter. But I think it has to be said that this was probably one of the key things that was criticised really when CP1 was first released, and as you can imagine, it's been a hot topic in the revision of the document. And so I think this has gone around the houses numerous times, but it's come back with that CP1 2020 will look to guide people towards the maximum velocity for a particular type and a particular pipe size. So that velocity method will, by giving you a maximum velocity, then it allows you to select your pipe size accordingly as you go on, and hopefully that will lead to better outcomes, because you know, the smaller pipe sizes, less heat loss, etc., as we go through, and that really helps the efficiency of the network. So we can work our way back through in my little hypothetical design here, applying the appropriate diversity factor as we go. So we know we had a diversity factor for 4 here, and then 8 on this leg, and 12 and 16, and so on, as we go back right the way through the network until these two sides here join, and we get to the energy center, by which point we should then have a total diversified flow rate for the network as a whole, and we can then start to turn our attention to the energy center, which is where we are now, really. So when I think we come to the energy center, the first stop off point for us really is to look at the buffer sizing, and I think it's important really to just thinking before we start and kind of dive into this about why we might need a buffer vessel on a heat network, and whether we do or don't need a buffer vessel on a heat network. I think in the vast majority of cases, in my opinion anyway, I think, you know, opinions differ on this, but I think in the vast majority of cases, a buffer vessel is certainly required and certainly beneficial. It's really there to deal with the peak domestic hot water demands that come onto the network, which tend to be transient. And I think if you ever go to a heat network where there isn't any buffer vessel, what you find is that the heat generating plant, be that peak load boilers or whatever, is typically in just disarray. You know, there's no strategy going on. And what happens in reality is that when a demand comes onto the network, the flow temperature starts to drop down a little bit, and the BMS says, okay, let's bring on a boiler. And the first boiler thinks about it for a bit, maybe goes through its pre-purge, lights up, comes in on low modulation, perhaps for a period of time, and then slowly starts to ramp up. And by this time, the temperature on the flow has already dropped further down, and the BMS is saying, okay, bring on another boiler, bring on another boiler. And before you know, there's, you know, all of your strategy is gone. All of your boilers and things are on when they shouldn't be, and just complete disarray, really. And that's very common if you go to heat networks where they've not employed a buffer vessel. So the buffer vessel helps cope with those peaks in demand, and also makes it a lot easier perhaps to work a proper strategy on your heat generating plant. Now, 10 minutes has been a typical value to size your buffer vessels around. You know, I see differences there. People would perhaps sometimes reduce that if they're struggling to get capacity in or whatever. But 10 minutes has been a typical value to take for many years, I guess. But we have to be realistic about the energy that we can actually get out of the buffer vessel. And we say, okay, as a rule of thumb, we'll say that we can't get more than 2/3 of the buffer capacity at any one time. And so we end up with this equation here of 900 seconds, looking just at the diversified domestic hot water demand. So that was the left-hand part of that equation earlier. We're not interested in the heating, because you know, if the heating drops off for a short period of time, then nobody's really going to notice that, but you will probably notice that drop in temperature if you're stuck in your shower and the hot water starts to dip a bit. So we're interested in just that domestic hot water size. So my simple example here, I plugged my data into the equation, and out I came with a 100-litre buffer vessel, and away we can go. Now, thermal storage, we've looked at it here just to coping with the peaks, but thermal storage might be needed for other reasons within a project like this. Maybe you've got heat generating plant like CHP that has minimum run times, or perhaps heat pumps and things that you want to build up some buffering capacity to stop them cycling all the time. So you may need to think about that as a whole, you know, separate to what you're doing with this particular calculation here. And again, I think Chris Parslow's guide's got some very good sections in this area. So if you're looking for advice around that, I'd perhaps direct you in that way, because like I say, it's very good, particularly in this area of thermal stores. So once we've got our buffer vessel together, we can start thinking about heat generating plant, and in this case we're looking at the peak load boilers. You know, what do we need to be able to pick up the demand here? Well, again, in my simple example, I've said that we need to cope with all of the heating coming on together, and of course if we were diversifying that, we would add that diversification factor into this section of the equation as well. But what you realize is that once we've got the buffer vessel in place to cope with the domestic hot water demands, then all we actually really need to do is reheat that buffer vessel back up within a reasonable time period. And a reasonable time period has typically been taken as an hour. And I've never really seen anybody have any difficulty with that, but you will see some variance on this. Sometimes my colleagues in Germany actually design around a half an hour there. Just the way their market has developed, I think, and seems to be the norm. But as I say, I've never seen anybody have a problem with that. So you can plug in your values that you've got for your scheme, and out we come with a value for the kilowatt requirement that we would need for our boiler plant in this case. Some things to say about this though, really. The first thing is that is the minimum requirement here, and it doesn't include any redundancy in this figure, and so we need to think about how redundancy is going to be tackled on your given project, whether you adopt that in perhaps a normal way that you would do with a redundancy, or if you adopt some other strategy, but it certainly needs to be considered. The other thing is really that when you look at plant, it's really important to think about how the network will operate through the year. And because if you look at like a demand profile from a heat network, then you see that typically they will be operating for under 25% for perhaps more than half of the year. And so when you're selecting plant and equipment, you need to make sure that you can get good turn down, and that you're going to be able to operate at those low demand points. And I think there's often I think a lot of experienced heat network designers are often much more focused on the low point and getting the low demand point correct right the way through their design, rather than focusing on the peak, because this is the low points that tends to be operating more, and that's where a lot of the problems tend to stem from. So really important that you get good turn down. That could perhaps be through cascaded smaller units, or having boilers that have got very good turn down individually. I think the things to avoid are perhaps getting very large boilers that are then going to really struggle during the summer months with lots of cycling and things like that going on. So really important to think about all of your plant in that way, that it's going to match the demands, because you will see lots of periods where the network will operate under 10% of its peak through the year, but we're talking about something that's got to operate 24/7 here, so really important. So we looked at the basic bits and pieces of the energy center, but of course, one of the key reasons to use a heat network is that we can perhaps adopt it to renewable technologies a little more easier than perhaps it would be to be trying to adopt renewable technologies at the individual dwelling level. Sometimes that can be quite challenging, but you accumulate them together, and having a much larger system can be easier to deal with. I think it has to be said really that over the last decade or so, that CHP has tended to be the bedrock of low carbon energy into heat networks. But I think as we go forward in a kind of a world of SAP 10.1, where the electricity grid is decarbonizing very quickly, CHP looks to be very challenging going forward in carbon terms, and I think we're much less likely to see CHP being the key heat energy generating source as we go forward. I think probably the default will now go to heat pumps, because that tends to be perhaps the next technology that could be applied, you know, a little bit more easy. There are still some challenges with that, though, without doubt, and we'll perhaps talk about that a little bit more in the next slide. I think if you look to, you know, government aspirations, then certainly they would like to see a lot more waste heat going into heat networks. It's, you know, one of the unique features about heat networks is that they could, you know, use waste heat as their main source or supplementary sources. And I think if you go back historically, then waste heat was probably the catalyst for heat networks being produced in the first place anyway, and so it naturally sits there. But I think, you know, for a lot of the smaller heat networks that we've tended to be dealing with over the last decade or so, because of, you know, policies have perhaps not been able to create an awful lot of the really big citywide heat networks to date, but let's hope that changes. I think trying to incorporate waste heat in smaller heat networks is really challenging. It gets more practical as we come up to the size of really big district heating schemes, of course, where you can, you know, much easier to perhaps inject that heat into the network as a whole, and you've got the kind of capacity there that can just can deal with that. But certainly a lot of aspiration from government on this, and I think, you know, certainly if we look to what the Green Heat Network Fund is looking to put money into, then this is the kind of area that they would certainly want to support. One of the other technologies, I guess, that's gone out of favour really is solar thermal. Seems a bit of a shame, really. I think going back a decade or more, we actually were involved in a lot of heat networks that used solar thermal. Seemed to work very nicely, actually. It was a very nice match in terms of the way that it could be used in heat networks. I think, yes, it's got put in the too difficult to do bucket, to be honest, because it can be quite difficult and challenging maybe to employ at times. But a bit of a shame, I think. If there's ever opportunities, then I would say don't dismiss it. You know, think about it to see if it can be used going forward. Just a little bit more about heat pumps, really, because one of the things that CP1 has always pointed out is that there is, you know, a case for thinking about hybrid systems here with heat networks, and thinking about the impact that this can have on the capital cost of your network, because it makes no sense really to have all of your peak demand and maybe a redundancy as well built into, you know, expensive heat pumps that is really going to bump up your capital cost. And I think there is some genuine concern here from government as well. You know, I've seen from BEIS that there's concerns that maybe these higher capital costs would just push some heat networks into the kind of not being viable zone, really. So it's certainly something worth considering is about hybrids here, because what experience has shown that typically with a coverage from your heat pumps of around maybe 40 to 60%, depending on the heat network that you're doing, then you can actually cover the vast majority of the kilowatt hours under this graph here. You know, you can cover maybe 80 to 90% of your kilowatt hours just by having a smaller proportion of your heat demand actually picked up through heat pumps there. So, or sorry, your peak covered by heat pumps. And then on the small number of days when you do really need these high outputs, boilers can kick in, pick up the demand, and, you know, probably at times anyway, where if you've got like air source heat pumps anyway, they're not going to be operating at their most efficient anyway. So worth considering. Still the message in CP1 around that. And you know, can have quite a significant effect on your capital costs. So I'm just going to finish up with a few quick hints and tips on refining the design. First one is around variable flow pumping, and I have to apologize here because this was put together, as I said, back in 2015 really. So I can't imagine anybody not doing a heat network these days without variable flow pumps. I think the points I would like to make on here is that it's important when you come to pump selection that you think about the same thing that you need to think about with a heat generating plant, i.e. that it's going to be operating at low points right the way through for, you know, big periods of big chunks of the year, really. So when you come to select your pumps and you're looking at efficiency, select pumps that are, you know, have got good efficiency at these realistic operating ranges. Really, it's no good having a pump that's absolutely fantastically efficient when it's running flat out at the peaks. We need to be looking at something that's much better at the lower end point. The other thing that perhaps comes up very regularly around pumps is about concern about minimum flow rates on the networks. Because we're talking about something that's operating 24/7, there's obviously concerns about, okay, you know, what do I need for my pump here, etc. I think there's all sorts of various strategies here, and it's good to have a chat with your pump manufacturers, of course. Typically, these things work through stage pumps, perhaps sometimes employing a smaller jockey pump to just pick up the lower demand periods. Perhaps, you know, when you're operating at midnight in July and there's hardly any demand on the network, these can kind of kick in. Chris Parslow's guide has actually got a very good design as well for a bypass adjacent to the pump that's controlled properly through differential pressure feedback or through flow metering and that type of thing. So it's another strategy that you can look at there. But I would also say for smaller networks, think that there is actually always going to be some minimum flow through if you've got summer bypasses on the network anyway. So that will account for some minimum flow. And a lot of the very good kind of modern pumps really are much more tolerant to no flow conditions, I think, than they ever used to be. Probably one of the key things to think about when you design a heat network is to have a strategy of how you deal with differential pressure control on the network. I think if you go back historically, there's been all sorts of different methods employed here. If you look at some of the documents historically out there, but I think the key thing that you're trying to avoid here is that all heat interface units will have some control valves that are controlling the flow through the unit, and they will all have some kind of maximum differential pressure that they can withstand. And if you go above that, then you start to get pushed by through the valves, and you start to get things like phantom meter readings going on, where people going away for the weekend and then coming back and find they've used energy when there's nobody in the apartment. And also that can lead to damage maybe of your HIU and things like that. So you need some kind of strategy. And I think the most common way of dealing with that these days is perhaps around, you know, good dimensioning of your pumps and well set up, maybe not on constant pressure control so much these days, because I think there's been some learning going on there from pump manufacturers, and they tend to operate more on proportional these days. But well commissioned, well set up pumps is the absolute bedrock of this. And then I think a lot of designs employ differential pressure control valves that are actually adjacent to or inside the HIU, so that they're directly protecting these control valves, which are then really the things that are controlling the flow on the network ultimately. So it seems to be a good strategy. It's pretty straightforward to commission because these tend to be preset, etc. So you get your pumps correct, and away you go really. And then finally, we talked a lot about heat losses today, and of course insulation is very important on a heat network. And I think, you know, when it comes to something that's operating 24/7, we have to think about what is appropriate. And for many years, people have used this standard BS 5422, but I think it's definitely been found that that's not appropriate for heat networks. It's really designed for standard mechanical situations. And so there's been a lot of debate about this within the revision of CP1 2020. And to cut a long story short, the CIBSE have decided to come back with thicknesses of insulation for given pipe sizes. So there will be tables in there. And this is quite thick insulation, really. So typically it will be either 50 or 65 mil thick insulation, which in itself needs to be considered when you're thinking about pipe runs, etc., because it's very, very large. But certainly 5422 not appropriate, although I would say with one caveat that it's actually up for review at the minute, so we'll have to see where that goes in the future and whether they change it around so that it does become appropriate for heat networks. But I think, the key thing that you see time and time again is that you go to heat networks and people put in just like they're doing it on standard mechanical design, whereas you need to be close jointed so that you're covering all of your valves, fitting, flanges, pumps, everything should be tightly insulated right up to the HIU so that you minimize those temperatures to a minimum, really. Yeah, there is other guidance out there as well, but I think the guidance in CP1 will be a good starting point for trying to improve that. So quite a lot of things there really to think about. As I said, this has really been designed around people coming to heat network design for the first time. I think there are really significant changes coming with CP1 2020, because particularly around this whole idea of acceptance testing and making the whole standard much more technically verifiable. I think that naturally that will have a bit of an impact on anybody involved with heat networks and how you build out heat networks going forward. But I think in the long run, it's imperative that we really start to tighten up on design and get good outcomes going forward, really, because when things do go wrong, it can be pretty bad outcomes for tenants. Well, a colleague of ours actually had to take an apartment over the summer period for a while in a Birmingham scheme on a heat network, and things had obviously not gone very well there, and the temperatures within the building, they could not get it down below 28 degrees with windows open and everything. So it can be pretty uncomfortable if you're stuck in a situation like that, and it really does highlight the need to get things right from the start. So okay, I see that I've heard a lot of pinging going on in the chat box, Angus, so I'm assuming there must be some questions in there, but I can't see them from where I am.
No, that's fine. Yeah, we've had a fair few bouncing around. Most recent one that's just kicked in from Nick, asking whether there was any technical reasons why you couldn't utilise I suppose a current or new district heating network to provide heat to a 5th gen ambient loop. No,
I think 5th generation. Obviously, we haven't touched on that at all here in this CPD, and I think. I think it is a separate topic, really. It's, from what I've seen of it, really, and involved in it, there's still, there are some interesting examples out there, and it looks very interesting on paper, definitely. And there's a lot of general interest around it. I personally think it's still early days. I would like to see a few more examples and more data on how they really stack up long term, both in terms of reliability and getting them operating well. I think there certainly does seem to be a case for them where you've got good balance of cooling loads and heating loads, and you can have this kind of prosumer situation going on. But yeah, I mean, it's a whole nother topic on its own, without doubt. 5th generation, yeah, I think our point of view is currently that we need to see a little bit more of it and see how it pans out.
Great stuff. It was also touched on a bit earlier as well as to whether there was much reference of 5th gen within the new CP1 2020. Yeah,
there is a as I remember, an appendix been put in just purely on 5th generation, which I think Phil Jones has put in, I believe. Because he's a big advocate of the 5th generation.
All right, stuff. We were just then touching on one that I suppose we get asked quite a bit in these sort of presentations on domestic hot water storage. Sort of within apartments, be it both either with HIUs or be it with heat pumps.
Okay, I think. As a general thing, storage on a heat network is, I don't think, personally a good thing to do. I think we've seen that from Scandinavia, really, that it does significantly add to your heat losses, and I think they have tended to come away from storage. There was a document or guidance note put together by the Hot Water Association a few years ago about heat network design using stored water. if you're looking for some guidance on it, you could maybe look at that guide. I think it's there are one or two interesting things you can do with stored heat now, storage like that. But my personal view is that I don't think there's enough evidence behind that particular guide to really give you a lot of confidence in it. That's my personal opinion. But I think overall, okay, when you're talking about storage situations with heat pumps, etc., maybe you're talking more about perhaps some 5th generation heat networks where you've got, boosted ambient loops and then individual heat pumps with storage for your hot water there. Yeah, I think that, how that all pans out long term, in what you do with that and how that really works out for schemes, because typically you've got all of that maintenance attached with unvented cylinders and things like that as well to consider. Whereas if you're just using HIUs, then typically you don't need to go and visit them any more than every 3 years is BSRI's guidance around that, and we tend to adhere to that ourselves. So yeah, there's lots of factors, but hot water storage, I think, in my opinion anyway, and I think and that, quite a lot of the industry thinks that doesn't really give you good outcomes longer term.
In the new CP1 2020, is there any advice on network allowances for future developments?
There is some sections in there kind of helping to deal with phasing of networks. I think it's one of the difficult areas really that you can come up against when you're dealing with big systems is around phasing. There is some general advice. I don't necessarily think it goes into a lot of detail, but and some of these things tend to end up being so project specific that sometimes it can be a little bit difficult to give good simple overarching advice about it really. But yeah, it certainly is a problem area, and there's a little bit in there about it, definitely.
Great stuff. Bit more of a heat pump specific query here about whether you would incorporate inverters on heat pump motors.
Oh, that's a difficult one. Really depends on your heat pumps and their efficiency and how you use them and the whatnot. Really, so I think I think there's a lot of variety in heat pumps out there, and a lot of it comes back to your operating temperatures. I think the overall, and this is a very simple answer and it sounds like a cop out, but it's really trying to get the right heat pump and the setup for your particular operating conditions and temperatures that you're dealing with really, and it's that kind of marrying those together I think is the key thing. But in terms of coming back to my earlier point, I suppose, around thinking about whole life costs and how that factors in, then I think if there's an argument for having slightly higher capital costs at the beginning, which are going to give you good outcomes, as long as that's within the predicted service life of your plant and things like that, then yeah, well worth considering.
Great stuff. I think we're rounding off most of the questions. There's one that's always an interesting one that's touched on the gap between performance and actual outcomes on systems. Are we seeing that gap closing down, or is it still a big uphill battle, I suppose, for CP1 2020 to try and sort? Yeah,
I think it's early days. Obviously, the new guidance not even out there yet. I think if you look to some of the larger network operators and some of the perhaps consultancies that have got the most experience with heat networks, then I think you're starting to see some really good examples of good outcomes and how to get to those. And I think certainly there's been a lot of effort within the next version, CP1 2020, to really capture some of that guidance and some of the core starting points for getting good, regularly good outcomes out of heat networks really. But I think a lot of it just comes down to some of those basic principles that I've tried to kind of touch on today, and it's just it's getting that expert advice if necessary in at early stages and things, which I think a lot of people are starting to do now. And let's hope that that performance gap will start to narrow, because I think it's vital for the industry. You know, I see government sitting in the background thinking about this regulation and where it's going with things. I think, I'm not going to say the clock's ticking for heat networks, but I think there's you know, they will get to a certain point where if heat networks are not giving good outcomes for tenants, and they've still got consumer complaints coming, then government will inevitably think about its strategy going forward. So I think this is a really important time now for heat networks over the next decade.
Absolutely. I think that's covered everything. Anyone is just, you've seen a slightly more up-to-date version of CP1 2020, whether there was any new or extra references to hydrogen solutions in there?
Yeah, it's mentioned, but I think you know, it's been kept fairly agnostic. But yeah, try our CPD on hydrogen. We can give you a good overview on it then. That's the next
Good
one,
answer.
maybe.
Oh, just had one more pop in. Which is an interesting one. For I suppose looking at strategies with heat networks, would we use modular boilers with different outputs, or look to keep that as one steady, simple output on all the individual boilers?
I think typically we've gone with similar outputs, because then it helps your redundancy, because you know, if one or two plant go down and perhaps your smaller ones go down, and you're left with the larger ones that are trying to cope with summer loads, and that can be difficult. So I think typically we've tended to you know, just have the demand in that way. But it really depends on the sort of scheme. You know, once you're starting to get into really big schemes, megawatt size boilers and things like that, then of course there's different strategies there, and you know, how that can be employed, definitely.
Always an interesting one, especially when you've got multiple energy centres. I've seen a few schemes that have worked with that on district heating projects, and trying to balance the differences with energy centres, with perhaps smaller, better modulating boilers that are used at certain times of the year, and then perhaps some larger, more sort of workhorses, so to speak, being utilised when it comes to the winter months.
Yeah, definitely, I guess, yeah.
Great stuff. Well, I think that rounds off all the questions we've had in the chat, unless anyone else has got any last second ones for us they want to throw out there. Otherwise, thank you very much, everyone, for your time. It's been really appreciated, you guys letting us talk to you today. Julian or Angus, do you guys need to say anything else before we bid everyone adieu?
No, just other than thanks very much. Thanks for the thanks to you guys for providing the CPD, and we'll send CPD certificates shortly, and look out for we're going to do a little survey of the participants, just to see how you enjoyed it, and whether you'd like to get involved in future CIBSE Home Counties North East or other CIBSE activities. So that's it from me. I don't know if Angus, you had anything to add. Don't think so.
Thank you very much. On behalf of Home County North East, we hope to see you soon on the next month CPD. Thank you.
Thank you.